Hello everyone. So in this video we are going to discuss about the property of differentiation and integration in the context of properties of continuous time Fourier transform. So what we'll do, we'll try to get the Fourier transform of a signal which is differentiated or integrated in the time domain. So from the previous notation what we have seen that we have a signal xt, its Fourier transform is denoted by x of j omega. And from the inverse transform equation we can write xt is equals to 1 over 2 pi integration minus infinity to infinity x of j omega e raised to the power j omega t d omega. Now we'll differentiate on both sides. So what we'll do, we'll take the differentiation on the time axis as d of xt over dt, and that will be replicated on the right hand side as well. So that will be d by dt of 1 over 2 pi integration minus infinity to infinity x of j omega e raised to the power j omega t d omega. So the differentiation is with respect to the time, so it will be equal to 1 over 2 pi integration minus infinity to infinity. This term will give us e raised to the power j omega t d omega, and the rest part will be j of omega x of j of omega. So this is the differentiation of this function, and what is basically happening is d by dt of xt is having a Fourier transform which is j omega multiplied with the earlier Fourier transform of x of t. So x of j omega was the Fourier transform of xt, and if we differentiate in the time domain, we'll get a Fourier transform multiplied with the factor of j omega. So what is happening here? Differentiation in time domain is equivalent to multiplication by j omega in the frequency domain. So a differentiation property is converted into a multiplication property by taking its Fourier transform. So this is very popular property of the Fourier transform, and that can be widely used also. Now we'll see the integration property. So integration property says that if we have a signal xt and if we take the integration in time domain, so we'll take x of t dt. So its Fourier transform will be 1 over j omega x of j omega plus pi x of 0 del of omega, and this extra part is basically arise because of it is a DC or average value that can result from integration, So this is your DC or average value or some constant value. So these are the formula for differentiation and integration, and let's use it to get an idea by solving an example. So we will solve and get a Fourier transform, very popular signal, that is u of t, that is unit step function. So we will take xt as u of t. So we all know that the unit step signal is having a value of 1, t is greater than 0, and it is having a value of 0 for t less than 0. And we all know that ut can be expressed as integration minus infinity to t del tau d tau. So if we integrate or take the running integral of your impulse signal, we will get the unit step back. So there is a relation of integration between unit step function and unit impulse function that is already derived in one of the previous video. You can watch that video again. So now we know that our xt is having some form of integration, and we'll replace gt by some general function g tau d tau. So if we'll take the Fourier transform, what will be the output? Output will be x of j omega, that will be equal to g of j omega by j omega plus pi g0 del omega. So what is g j omega? So here our g function is your impulse function. So we all know that g of j omega will be 1 for all frequencies. So the Fourier transform for delta function is equal to 1, that is every frequency is contributing equally. So now replace all the values, so we'll get 1 over j omega plus pi del of omega. So this is your Fourier transform of unit step signal, and that is calculated using the property of integration. Now unit step is integration of your unit impulse, that directly infers that unit impulse can be written as derivative of unit step function. So can we get our Fourier transform of our unit impulse function back? So yes, we can have it. So we can write del t as dut by dt. So we have already derived the Fourier transform of ut, which is represented by this equation. We have to just multiply it with j omega to get the Fourier transform del t, because this is the derivative of unit impulse unit step signal. So it will be 1 over j omega plus pi del omega, which is equals to 1, because this factor is multiplied with this, it will give 1, and when this will multiply with this factor, it will give 0, because impulse will multiply it with this function and it will sample the function at omega is equals to 0. So we are getting our impulse signal back. So these are the property for differentiation and integration. So next we will discuss about the time and frequency scaling property of continuous time Fourier transform. So what the property states? The property states that suppose xt is a continuous time input signal and it is having a Fourier transform of x of j omega. So suppose we scale the input function with a factor a. So suppose we have x of at. So the effect of this scaling at time domain is given by 1 over mod of a x of j omega divided by a. So this is the time and frequency scaling property. So let's see how it is derived. So we have our expression for Fourier transform of x of t, which is given by integration minus infinity to infinity xt e raised to the power minus j omega t dt. Now what we will do? We will scale our input with a factor at. So now what will the Fourier transform of this factor? We have minus infinity to infinity x of at e raised to the power minus j omega t dt. Now in the next step, what we will do? We will replace our at with a factor tau. So this change will be given by integration minus infinity to infinity 1 by a x of tau e raised to the power minus j omega by a tau d tau, and this will be when a is greater than 0, and if a is less than 0, what will be the output? Output will be minus of minus infinity to infinity 1 by a x of tau e raised to the power minus j omega by a tau d tau. So when we will closely look this form, it will resemble this form. So in this manner, we can say that when we scale in time domain, we will get an output of 1 by mod a x of j omega by a in the frequency domain. So what this factor is showing? So we have our factor x of at Fourier transform gives 1 by mod a x of j omega by a. So there is first is that we get an amplitude factor of 1 by a. So we have an amplitude factor here. Second, what it says that linear scaling in time by a is equivalent to linear scaling in frequency domain by 1 by a. So, linear scaling in time by a, this is the factor a, is equivalent to linear scaling in frequency by a factor of 1 by a. This is quite visible here also, that we are scaling with at and we are getting omega by a. And another inference from this property is that we have an inverse relationship between time and frequency, and that is quite obvious. So, we have an inverse relationship between time and frequency. So, a common example is that suppose we have a sinusoidal signal and we increase the period of that signal. What will happen? The frequency will decrease. And one quite obvious effect of scaling is that suppose we have got an Fourier transform as 1 which is having value mod of omega varying from minus w to w and 0 otherwise. So, it is kind of a square rectangular function, square or rectangular function. So, here what we will do, if we will increase the w, so if the width of that wave is increased, so the inverse Fourier transform of this x of j omega become narrower and taller. So, in time domain it will be a narrower and taller. So, there is a shrinking happening in the time domain, and as we all know that suppose this rectangular function approaches to infinity, what we will get? We will get an wave which is varying from minus infinity to infinity having a value of 1. So, now we made w to increase till infinity, and we know that the inverse Fourier transform is delta. So, like that, if we increase the period in time domain, then it will be equivalent to shrinking the frequency and vice versa, that is having an inverse relationship between time and frequency. So, this property stated clearly. So, in this video we discussed two properties, and in the next video we will discuss the property of duality.